Waiting for the confirmation. It's all good. All right. So what we'll do today is basically just to continue our discussion of function calls. So this time we'll start to combine, variables, parameters, recursive function calls, and stuff like that. So eventually we're going to move on to structures and pointers and whatnot. But right now we are still kind of right here. This is our lab for today, and so we'll go ahead and get started with all this good stuff. Are there any questions about the lab from the other day, from last Thursday? So are there any questions about the lab from last Thursday? Nope. Okay, so I'm assuming everything is good with that lab. All right, so we'll go ahead and continue, and this time we'll start to introduce local variables. Last time we already talked about parameters because I just watched the video from last Thursday. We talked about the subtraction subroutine where it has two parameters and it has to return the difference between the two parameters. So that's what we talked about last Thursday. So what we'll do today is to kind of add something to what we already talked about, and that is local variables. Okay? All right. So your homework assignment, your lab, is this one. It is called function calls. And if I give you a preview, it has a whole bunch of questions, but for the most part, it is really just a reinforcement of what we talked about in class, about all the standards that we have already been using. And this one would also go through, a particular subroutine, which is swap, which is fairly standard in C and C++ in terms of the code. But it will guide you through the whole process to write, the subroutine called swap, and so that you basically learn how to use local variables, or one particular local variable in this case, for swap. Is that okay? All right. So what we'll do today in class is to kind of make use of local variables, but not in this particular way because that's your lab. So we'll go ahead and write a program in C first, and then we'll translate that into assembly, step by step. All right, so let me see. I need mouse pad. Okay. So we'll do a very clumsy version of a recursive, subroutine. Okay. So this is main, the usual stuff, and it's going to call main itself has a local variable x. Okay. So this is the local variable, and then we'll say x equals 2. 5 plus 7, both are subroutines, and return 0. Okay, so we'll just use this as an example. This is kind of like the minimal of what we need to demonstrate, how to deal with local variables, and I also want to demonstrate how to use functions, at the same time. So then we have 5 as a subroutine defined only to return the value of 5, and then we have 7 only to return the value of 7. So is that okay so far? Okay. So to make your compiler work, this program is not going to compile without some complaints from the compiler. Because from the compiler's perspective, by the time I call 5 and 7, there's no declaration nor prototype for those particular subroutines. In other words, the compiler says, hey, I cannot check whether you're using the return value of 5 correctly. I cannot check whether 5 is getting all of its parameters or not. So in order to make the compiler happy, when you write this in C or C++, you kind of have to do this extern int 5, and then also extern int 7. All this is doing is telling the compiler and say, yes, I know there is a subroutine called 5. It doesn't take any parameters, and it returns an integer. And yes, I also know that there is a subroutine called 7. It is not defined yet, but the subroutine 7 is going to return an integer, and it also does not need any parameters. So that's what the first two lines are telling the compiler, so that when the compiler does get to line 6 in main, the compiler won't complain anymore because it knows that, okay, I see that you're using 5 and 7 correctly according to the prototypes. So this is strictly not a topic for assembly language programming, but I just thought that, it's kind of useful to kind of bring it up, just in case, you guys were not exposed to the concept of extern, or the prototype, defining the prototype of a subroutine before it is defined. Extern is not necessarily needed in this case. In other words, if you just say int5 and int7, I think that will also work. So are we good so far with this code? Okay. So now we want to translate this into assembly. And let me see if I already have another mousepad. Yeah, I have plenty of mousepad here. So I'm going to use this one, for the translation into assembly language. So main is basically a subroutine, okay? So, but before we get into main, we say no op, because we might want to use the trace analyzer, and every time you want to use the trace analyzer, the first opcode has to be a no op. And then we want to initialize the stack pointer. Even though it's not strictly required, it is good to remind ourselves that the stack pointer does need initialization. So after that is kind of technically what is in main itself. So in main, we have a local variable. X is a local variable. So the first question is, where is this local variable going to live? Okay. It's not going to be a byte thing. Okay. We're not going to use the byte directive to reserve a byte statically and then say, okay, this is our local variable X. Okay. Let me just kind of show you what I mean by that. This is not the way to do it. So this is not the way to do it, because this is only going to allocate a byte, that is associated, where the address of this byte is associated with the label of X. But this is static, which means this is what you want to do if X is a global variable or a static local variable. But because I'm not saying static in the C code, it is automatically auto, which means it should be living on the stack. So that means this is not the way to declare X. Instead, what we'll do is we are going to say, okay, this is how I would define it. I would define a label X. But the definition of X is not the address of whatever is right after that. It is just a number. And that number represents, in main, at the entry point of main, where do I find X relative to where register D is pointing to. I hope that phrase rings a bell. Okay, where is X relative to where D is pointing to? Because that is one of the questions in the lab that you started last Thursday. Do you guys remember that? Yes? Okay. So we'll leave it empty for now. Okay, we'll put a question mark here and make sure that this does not assemble, okay, because we need to backfill that. But in order to reserve a byte, to store a local variable, this is what we do. Okay, so we'll just say reserve a byte to store local variable X. That's all we do. So you can see that, well, we're just decrementing the stack pointer. Yep, exactly. So we're just reserving a byte here. Okay, so after that, we can now call 5 and 7. So let's go ahead and put a halt here for now. Don't copy it because I'm going to have to insert a lot of code before the halt. So don't copy this. And I'll get started with 5 and 7. 5 and 7 are pretty easy to do. LDI A5, okay, LDBD, increment D, JMPB, that's 5. 7 is going to be almost exactly the same. Okay, so just copy and paste, change the entry point label to 7, and then return the value of 7, and that's it. Okay, and you can see that we are using register A in both subroutines to return the value, because that is the agreement between the caller and the callee, is the return value of a subroutine is always passed by register A. Is that okay? All right, so this is something that we have done and talked about already last week. So there's nothing new so far in this slide except for the fact that we allocated a byte for local variable X. So now we go back to local variable x and go like, right at this point here, okay, right at this point, which is right before the halt instruction, I'm done allocating everything that I need for the main subroutine. So where is x as a local variable relative to where d is pointing to? Can anyone tell me? 0. The stack pointer is pointing to local variable d right now. So I would use this to basically remember, okay, at the entry point, okay, of main, after allocating for local variables, the stack pointer points to local variable x. So there's a there's an offset of 0 from where the stack pointer points to relative to where x can be found on the stack. Is that okay? So now we get ready to perform this statement on line 6. So what do you think we need to do first on line 6? There are two things we can do. You can do it in any order you want. Yep.
Wait, I just noted that it's okay, but I'm actually not totally following what X.
Okay, so that's okay. When we make use of x, I think it'll be more clear. Okay, so right now I'm just saying that x is where the stack pointer is pointing to, because the decrement d allocates that 1 byte for x, and the d register d is now pointing at that location where x is supposed to be. Yep.
Is the colon in front of the X marking it as a label?
It's marking it as a label definition, which is needed. Yep. Because we are not referring to x, we are actually defining what x is supposed to be. All right. So yes, go ahead.
So if we decrement D first and then we say the label, it would be offset by 1.
It will still be the same. Because this particular label definition, is saying, okay, x is defined to be 0. So it doesn't matter where I put this label definition, this one over here, I can put it anywhere within this program and x will still be defined as 0.
How?
Because we have a constant expression of 0 in its definition. A label can be defined in two ways. If you just have an x colon without an expression after that, then x is defined to be the address of whatever is right after this line, which is the decrement instruction. On the other hand, you can always have an expression that is in postfix format, and then x, whatever the label is now defined to be whatever the value of the expression is. Yes?
But is that still, is X still a label pointing to the position of 0?
X does not point to anything. X is 0. It'll be more clear what I do with x later on. So for now, we'll just say that x is 0. Okay? With that, yep.
It's just the same concept as a prototype word definition. You put in front of the main just so like when it actually reads it, it makes sense.
It's a symbolic name so that instead of having me to mentally memorize where x is relative to where the stack pointer points to, I can now refer to the symbolic name of x. That's the whole purpose of defining the symbol x. Yep.
But will this assemble?
It will assemble. Yep.
So what's the difference between this label definition and x colon and a line just beneath that byte?
I just mentioned that. So if you have a label definition without an expression, without a postfix expression next to it, then the label is defined to be the address of whatever is right after it. Or you can say that it's defined to be the current location in the assembling process. So there's an implied, okay, how about this? This is the default. This is the default if you don't say anything, but you can also change it to any expression you want. If you don't say anything, okay, if you don't say anything, it is the same as saying x colon and then a dot. On the other hand, if you give it an expression, then it becomes the label is defined to be the value of the expression.
Okay, but what does that look like in like RAM? Because we can see it in the assembler, but like I don't know what that turns into.
Well, when we assemble it, we will see it. Okay, so just hold on for a little bit, until we get the entire thing written first, and then we'll look into the assembler and then find out, how the label is actually utilized. Is that okay? So just give me a moment here, finish the program first, and then we'll get back to, what it looks like. Okay, so right at this point, we are going to implement line 6 in the C code in assembly. So the first thing we need to do is to call 5, and then we call 7, and then we add the values of 5 and 7, right? And then we use that value to update the local variable x. Okay, so we already know how to call a subroutine, okay? It's decrement D, okay, to reserve room for the return address, and then we push the return address on the stack, which is usually just an LDI, whatever register A, B, or C, okay, not register D, with .5 plus, okay, we explained this one before, I believe, okay, and then we do a st instruction, store to whatever the stack pointer points to, register A, okay, which has the return address, and then we do an unconditional branch to the subroutine that we are calling. In this case, because it is addition, the order of calling these two subroutines is not really important. Which one do you guys want to call first, 5 or 7? 5, okay, we'll say 5, okay, so we JMP I to 5, and when the subroutine is done, it's going to return to whatever opcode is on line 11. Is that okay? So right at that point, okay, when the subroutine 5 returns to whatever opcode I have is on line 11, register A has the return value of 5. Is that okay? So, okay, so we got one call done. So you will say, well, we need the other one done too. Okay, that's pretty easy. Copy, paste, and modify. Okay, so now we have 2 calls, except we have a problem. Because register A right here, on line 12, when we perform decrement D, register A has the return value of 5, right, from calling 5. But when we are done calling 7, register A will now have the return value of calling 7, and it would have lost the return value of 5 because it's the same register. Now, can we use a different register? No, because it is the convention, okay? By convention, we can only return values through register A. So register A is the only register I can count on as the return value. Okay, can we move it to a different register? Okay, can we do something like this, CPR CA? Okay, so we make a copy of register A in register C. We call the subroutine again because now the return value of 5 is in register C. Well, you can, but it is a risk because how do you know that function 7 does not change register C? You do not know, right? Because you have to make the assumption whoever is writing the caller is not the same person who's writing the callee, nor is the source code available. In other words, it would still be perfectly okay if I go to 7 and I say, I've been using register B for too long, let's just change it up a little bit and use register C to store the return address. This is perfectly okay. There's no problem. I did not break any rules. But now the code won't work because because when we get back to main, register C will once again be clobbered by the subroutine 7. Yes?
Could we store it in RAM?
Yes. So the idea is store it in RAM, and there's a construct in RAM that we have been using up to this point that we just basically stash everything that we want to store over there. What is it called? The stack. Yep, exactly. So instead of putting the return value of 5, calling 5, into a register, which can be clobbered by calling another subroutine, we just say, we'll push it on the stack. Because a subroutine is not supposed to mess around with things that it does not own on the stack. Okay? Now, note that I said not supposed to, doesn't mean that it cannot. So we'll store it, okay? Which starts with decrement D to reserve the space. And then this time it's pretty easy because we just do a stda. So now we push the return value of 5 on the stack. Now, once something is pushed on the stack, it is supposed to be safe, okay? No subroutine is supposed to mess around with this. Are we good? Okay? All right. So now we're coming back from 7 at this point, and I need to perform an add because that's what the C code is calling for, is I need to add the return value of 5 and the return value of 7. So I know I need to do some kind of add. I also know the return value of 7 is already in register A. So that's kind of cool. All I need to do is to figure out what was the return value of 5, and then if I can put it into register B, that'll be perfect. Is that making any sense? So now I need to figure out, how do I get this to happen? How do I get B to be the return value of calling 5? What do you think? We pushed that onto the stack earlier. So what do we need to do now? We pop it, okay? Pop is the opposite of pushing. So what we need to do now is to say, okay, do a load into register B, whatever the stack point is pointing to, and then we do a increment D to deallocate that spot. Okay, I hope you guys remember this is the pop operation. Okay, we retrieve first and then we deallocate, and then the opposite is push, which is allocating first and then we store onto the stack. Is that okay? Yep.
Why can't you just assign directly from the stack?
What do you mean by assign directly from the stack?
So like the load from B, just get that the value that D is pointing to and add it to A. Can you do that directly?
You mean something like this? I wonder why. Can someone answer that question? I know some of you are thinking, but you are the professor. You're supposed to give us the answer. No, that is not the case. I'm supposed to help you figure out the answer. I'm not supposed to give you the answer itself. Yes?
Is it because these are matches, not the actual value?
Correct. So there are several things, okay? First of all, the assembler is going to bark or barf, okay, and say, we cannot do this, okay? But that's artificial. That's just syntax, doing its thing, going like, no, we don't recognize this particular way of specifying the second operand of add, okay? So that's the first thing. But let's say we relax the assembler so that it would actually accept this format. What type of opcode do you think is going to assemble it to? So that goes back to the opcode table. Okay, the opcode table defines every operation that is currently supported in the ROM. Okay, so we go to the opcode table. Now this is a good question, okay, in a sense, because this is what you need to think as well when you encounter something like this is, well, can we do this particular combination of operands, okay? The answer is no, but why not? So when you look at the add operation, there's only one operation here that performs addition. It is this particular one, and we'll zoom in a little bit so we can read better, okay? So when you look at this, what is it saying? It says it is not adding what y points to x, it is adding what y has to x. Is that okay? So in the C representation, it says x plus y, not x plus asterisk y. Is that okay? Then you go like, but we can change this, right? We can just change the syntax or maybe add a new opcode, then it'll be done. Well, if you look at this opcode here, which is 8, and then XX is one register, YY is the other register. When you go to that slice of microcode, you will see that it is going to connect register XX to in1 of the ALU. It will connect register YY to in2 of the ALU, not what YY is pointing to in2. Okay? Then you go like, well, can we make a new opcode to get it done? So to answer that question, you will have to bring up Logic Sim because you need to look at the diagram. Let's see, I'll just get rid of this stuff here because all I need to do is to look at the processor. So the question is, can IN2 be connected to RAM where the location is pointed to by another register, let's say the register that connects to out1? And you will find that there's no such path. Such a path is not possible. So that means, given the architecture as it is right now, it's physically impossible to have an operation as what we try to do, which is adding, dereferencing a register to a register. It is just physically impossible. Is that okay? That is how I want you guys to think about it when you say, well, can I just do this? Well, go through this process, okay? Is the architecture even supporting that type of operation? If the architecture cannot support that type of operation physically, then the answer is a hard no. It simply is no, okay? On the other hand, if the architecture does support that path, it is just that our current opcode does not have one to configure that particular path or that particular sequence of operation, then there's a potential of adding a new opcode to get it done. Yep.
Are there operating that do that?
There are architectures that can do what we just mentioned. The answer is yes. They're usually called CISC architectures because it is not required. Because, to do something like this, which is kind of like, it would be kind of neat to do it. In fact, it would be neat to do it this way. Combine the auto increment into the one instruction. And there are architectures that can do just that too, okay? But we can do the same thing just by this. Instead of using one single opcode to do it, now we have 3 opcodes to do it. But it accomplishes exactly the same thing. Is that okay? Can everybody tell, can everybody differentiate, the one single opcode versus the 3 opcode approach? So now the question is, which approach is better? Okay? And better is a very bad word because it is not very specific. Is it better for the programmer? Is it better for the silicon, the manufacturer? Is it better for the data center who will be making use of this processor? So better for whom? That is the question, okay? So let me answer those 3 separate questions, okay? From the programmer's perspective, yes, it will be more convenient if we can just say add A in open parentheses, D++ close parentheses. It's just handy to be able to do that, okay? Up to a certain point. Because if you add addressing modes and if you add capabilities like that, then you have all kinds of combinations of addressing modes and whatnot. So now you have to start to remember, whether a particular combination of addressing mode is supported or not. Whereas in the RISC architecture, this is pretty easy. If you want to add, you can only add between 2 registers. That's it, okay? There's only one instruction that can load the content of RAM into a register. There's another one to store a register into content of RAM, and that's it. That's the only way you can interact with RAM in this particular RISC architecture. So that's from the programmer's perspective. Second perspective, manufacturer. Okay, which way is better? If you want to support add A and then in parentheses B++, then your architecture is going to get more complicated, which means more silicon, which means the die size is going to increase. So why would that not be a good idea from the perspective of the manufacturer? More money and why does it take more money? There are 2 reasons, okay? It costs more per chip, yes, but why is that the case?
Well, dyes are super expensive to purchase too, so you have to purchase a whole new dye if you are using a small one.
Well, okay, so I'll show an example. This is somewhat extreme, okay? So let's say this is the wafer, which is the raw material that you use to make all the dyes, because So on one single wafer, you can make, a whole bunch of dies. I'm just going to use this as an example, okay? So all of these little cells, are individual dies, okay? And let's just say that this is a CISC type of processor. And then with a RISC architecture, it has less transistors. So now you have a higher density of dies, okay? All right? I think you guys get the idea. Okay. Wow, too bad. All right, so you would look at this and go like, well, if this is a RISC architecture, obviously from the same wafer, I can have more products available, right? But that's not even factoring in, some of these is going to be defective, okay? Everything has a, there are certain factors that will render some of these dies to be defective. So that has to do with, okay, let me use a different color of pen here, and I'll just kind of speckle. Okay, so I'm going to speckle 1, 2, 3, 4, 5, 6, 7 dots here. And I'll speckle, 7 dots here. And I'll have, let's see, what am I talking about? Right, so whenever there's a speckle, in a cell, that thing cannot be used anymore. But you can see that, the yield, which is based on what you can sell out of one wafer, the ratio of what you can sell versus what is on the wafer, the yield of a CISC is always going to be lower than the yield of a RISC. Okay, and that's a big factor because you can always argue and say, well, the CISC processors I can sell for more money because it's capable to do more, blah, blah, blah. But the yield is lower because you cannot, the proportion or the ratio of the ones they can sell versus the potential is always lower when you're talking about a die that is bigger than a die that is smaller, because the chances of a defect landing on one of these things is actually higher. Is that making any sense? So from the manufacturer's perspective, it is more profitable to manufacture RISC type architectures as opposed to CISC type architectures. Now that is without taking marketing into consideration, because when you consider marketing, it all has to do with what people are willing to pay for, right? So when you look at the super high-end i7 processors, they are much more expensive compared to the mid-end i7 processors. And that's only because people are willing to pay that kind of a price. But Intel or AMD does not make a lot of money from their super high-end products. They make most of their money from the mid to lower-end products because they sell a lot more of those than the super high-end products. Okay? So that's the second perspective. Third perspective, the data center. Okay? Google, Amazon, Facebook, they all have huge data centers to perform all the computations that they need to do. Right? Facial recognition, voice recognition, Alexa, those are all kind of compute intensive type of operations. So now the question is, okay, given a particular structure, but a particular building, how much processing power can you pack into that building? What do you think is the limiting factor? Let's say we are talking about the same square footage, okay? So we have implementation A, implementation B. Same kind of building, same kind of electrical hookup and whatnot. Okay, what do you think is the limiting factor? Okay, let me ask you a different question then. Let's say you have a LAN party. Okay, how many people have had LAN parties?
Like back in the days.
We still have parties. Yeah, still have.
Okay, so let's say you have a LAN party, okay, and it's a CSGO LAN party where the graphics card is really important. Everybody wants like a 20 gazillion frame per second type of setup, right? Because your eyes are faster than the eyes of a fly, and you can tell the difference between a 300 frame per second versus a 500 frame per second game setup. I mean, if someone actually made a video of what flies actually see in a room condition like this, where we see continuous lighting. To a fly, it's like light on, light off, light on, light off. Because everything flickers, okay? Fluorescent lights flicker like there's no tomorrow. This screen also flickers. You can see, my hand, flickers a little bit because there's a refresh rate to it, okay? But the refresh rate of the eyes of a fly is so high that it doesn't see constant light in this condition. It sees the flicker as on, off, on, off. And that's why it's really hard for us to kill a fly by swatting it, because it sees it coming, like in slow motion.
You sure it's not the wind? Like, when the thing.
The air pressure?
Yeah,
I don't think it's the air pressure. I think they actually see your hand approaching. You can design an experiment to find out too.
I smacked one.
What I usually do, I can smack one too. With the interesting about flies is the newborns they are not as responsive as the grown-ups. So if you have a fly that just became a fly, instead of a, how do you call those, a wormy thingy when they were younger. The maggots, right? So once they turn into a fly, the first, I guess, few hours, they still have to learn, how to flap the wings and how to respond. So they're really dumb and easy to get to. But once they grow up, after a while, they, for whatever reason, they just learn, how to, flap their wings in certain ways to evade, being killed.
You're saying you killed the level 1. You have to kill it.
Yep.
So why are we talking about flies?
Yeah.
Because you guys want the best setup for your gaming computer. Okay, so you have each computer has a 1,000 watt power supply, because it's barely enough for your super duper graphics card and your 16 core processor and your 32 gigs of RAM and your RAID setup that has like 5 SSDs and whatnot, right? Okay, and not to mention that everybody has a 30-inch curved monitor, at least one of those, if not two, so they have a full surround type of setup. Yes.
Do you have that set up?
No. My setup is right here. That's my setup. So now you're talking about 1,000 watts, for the main computer, right? And then about 20 watts or so for the monitor or something like that, which is insignificant compared to the 1,000 watt of your computer. So you have 5 friends, because a team has up to 5 people. Okay, so 5 friends, and let's just say that you're in your room and your parents are fairly wealthy, and you have a room of 15 by 15 feet all to yourself. Okay, that's kind of cool. I don't have a room like that. No, in that case, it'll be 50 by 50. Okay, so you have your friends bring all their setup, and everybody hooks up and power up, right? What is the first thing that's going to happen? Your breaker is going to break, right? The circuit is going to break, because think about it. You have 5 1,000 watt devices. So the room is going to consume about 5 kilowatts. 5 kilowatts divided by 110 volts is approximately, I'm just going to do an approximation here, approximately, let's say 40 amps, okay? And most room comes from one single breaker, if you're lucky. And if you're in one of the older homes, then multiple rooms will come from the same breaker. One breaker can only supply up to about 30 amps, okay? So when the 4th computer comes up, it's going to trip the breaker. Then what do? Oh, easy peasy. Since you have a wealthy parent, you ask your parent to hire an electrician to hook up a second breaker to the same room. So now you have 2 breakers into the same room, supplying up to 60 amps. Okay, so now you have enough juice to supply to that room to have up to 5 1,000 watt gaming computers. Not a problem. Okay, can be done. So now in the dead of the winter, when outside is like 29 degrees at night and whatnot, you have all your friends coming over, they all start up their computer, everything seems to be working, everybody is happy. An hour into the gaming, what's going to happen? Everybody is going to die from heat exhaustion. Why? Because it doesn't matter. It doesn't matter what you do to cool the computer in the room because you cannot get rid of the heat in the room itself. You say, Mom, I need to turn on the AC. But son, it's January, okay? It's winter break. We don't turn on the cooler. We don't turn on the air conditioner in the middle of the winter. But we are really dying here. Look at us. We are all sweating. We are dying here. Okay? Because 5,000, you can open the window, but you can only cool down so much because you're talking about, you know those electric heaters, right? Okay? It's like having 3 of those things, but not on a thermostat. They're on 100% all the time. And your room is 15 by 15 feet, which is a good size, but it's still not nearly enough because the heat builds up. Okay, the room, the size of the room is not really important because it just cannot dissipate, all that heat. Okay, so eventually, what limits how much processing power we can fit into a space is heat dissipation. How fast of the heat from computing. That is the bottom line. Okay. When you talk to Google, when you talk to Facebook, when you talk to Amazon, their infrastructure, the most basic constraint of their infrastructure is in terms of instructions per watt or instruction per joules per energy unit. Okay, it's about energy efficiency. It has nothing to do with the green movement or being environmental. It has to do with how much processing power can you pack into a space, into a fixed space. Okay, so in that case, as it turns out, RISC wins big time. Even though one processor cannot do nearly as much as one processor from the CISC, because remember, you need 3 instructions to do what a CISC can do in one single instruction. But the problem is, with a CISC processor, you have a lot of extra, transistors that really do not do anything particularly productive per clock. Okay, let's say, with a CISC architecture, the utilization of transistors is, let's say, we'll call it 15%, okay, which is a completely made up number. So that means, 15% of the energy is actually spent doing something meaningful. But a RISC processor may be, in the range of like 50%. That means, it's much better to have more RISC type processors than fewer of the CISC processors to get to the same amount of processing power. Is that okay? It's really kind of odd. It is counterintuitive because most people think, well, CISC should win because I can do so much more with one single instruction. Well, yes, but it is not efficient from the perspective of energy. That is the problem. Is that okay? So that brings us all the way back to why the TTP, the text toy processor, is a RISC type processor. Okay, because most of the devices that require assembly language programming are RISC type processors. They're not going to be CISC type processors anymore. The only CISC type processor that is still in production and being sold are the processors in your PC. Okay? Can anyone tell me what do you think is the projected growth of sale, when it comes to desktop and laptop computers as opposed to mobile devices or wearables? They're tapering off. Okay, desktops, even laptops are tapering off when it comes to sales. The next decade is all going to be not even mobile; it's going to be wearable, because they have already started to move in a direction to pack enough processing power onto a wearable. There was one, I read that news today. They're packing enough some processing power onto a contact lens. Yep. Sorry?
It's like Spy Kids.
Sorry?
Like Spy Kids, the movie.
Oh, Spy Kids? Yeah. Yep. So we are already talking, in that direction, and that's why it's kind of important to talk about, the differentiation between CISC and RISC, because it does make a difference. Yep.
It's a little off topic. But
Yeah.
how does the watts work? For example, I know crypto miners, they use a lot of power.
Mm-hmm. Yep.
A regular house.
Yeah, the amount of greenhouse.
They have specialized processors already to try to optimize. This is an article that you might be interested. If you want to look into like specialized hardware for specialized type of computing. So it's Google Neural Hardware Data Center. I think that should find the original article. There we go. It's an older article. It's not. It's pretty old. 2017, April 5th. So what Google did, because Google had to do all kinds of AI stuff, with image matching, voice recognition, and all kinds of stuff like that. Those are all neural net based. So before they built an AI chip that is specialized to do neural network computation, they just could not pack enough processing power into their existing data center. So what they did was they actually designed a chip. Okay, this is where computer engineers come in. Is the design of an actual chip that has a special purpose. By doing that, they are reducing the number of buildings they would otherwise need. Right here it says it saves Google from building a few dozens of new data centers. And we are not talking about small data centers here. I mean, those are huge data centers. These data centers are not what you see in pictures, where there are rows and rows of computers and servers, and you see people going in to service the computers. These are all going to be serviced by robots. The aisles are not wide enough for people to walk. How many people know what is a RAID? RAID? A RAID array, like a hard drive array. Okay, to have redundancy, okay, and also uptime. Those things, they use software to predict, how much time is left on a particular SSD. So before the device fails, they would swap it out with a new device. But it's not going to be a person who's going to do it. It's actually a robotic system that would go to the correct rack, go to the correct, slot, and then go like pop, take the SSD out while everything is still up and running, and then insert a new one back in. It's all done automatically using robotics. It's not a person doing it anymore. Yep. So this is the kind of setup that we are already looking into. This is now. It's not even science fiction anymore. Yep.
Pretty soon we'll be able to read minds.
Hmm?
Pretty soon we'll be able to read minds.
Not we, the computer.
Sponsored by Google.
Endorsed by Facebook.
Collecting data.
That may be happening already. If you think about it, if Google or Facebook is capable of doing that, through your camera on your mobile device or your laptop, if it can read your expression and know generally how you're feeling, and it can correlate that with what you're watching or what you're reading, if they have that capability already, do you think they will advertise to the whole world and go like, yes, we can read your facial expression and we kind of know what you're thinking when you're watching this particular image? Do you think they will let you know? They will never let you know. They will make use of that, okay? But they will never make you know. They will never let anybody know about it. So, so when are we going to know about it? That's a good question. All right, so getting back to the boring stuff. Yes, go ahead.
It's funny, sometimes we talk about something and then like on Safari or like when you search on Google, something similar to what you were talking about shows up.
Oh, they're always eavesdropping. There's, yeah. You can assume that they are always eavesdropping. But the interesting thing is, they never really advertise things that I'm interested in.
You should say it more often.
I don't think it has to do with that. I think different people have different thinking process, and they model, they use AI or neural network to model how a person would do things. So they want to cater to the peak of the bell curve, because that's the most cost-effective way to configure the software. So apparently, I'm not within the bell of the bell curve. Yeah, well, it has to do with personality types too. INTP are known as the warmest machines, warmest robots, and INTJs are known as the coldest humans. They're both, not at the center of the curve. If you ask a robot, what do you want? What do you think the robot is going to say?
More processing power.
Exactly.
Oh, sorry. I did not catch that.
It does not compute. Okay, so we're getting back to this. Let's see, where are we at this point?
Added the
Ask a robot why are fire trucks red.
Okay. Well, the answer is because red represents ripe food, and we evolve over time to recognize red as something that we should pay attention to. Well, for two reasons. Blood is also red, right? But ripe fruits are also red. So, primates, okay, evolve to have color vision so that you can forage food more effectively. You don't have to climb all the way up that tree only to find out, dang it, it's still sour. You just look and go like, nah, not gonna do it. And that by saving that energy, you improve your chances of survival. So that's why red kind of registers differently, compared to other colors to us. I think. It's a theory. Okay. All right, so at this point, we're adding the two return values, okay? Because one is in B, the one that we retrieve from the stack is in register B. A still has the return value of 7 at this point. So now the question is, how are we going to store this into local variable X, okay? So if you look at how I use the stack pointer, at this point, the stack pointer is balanced. In other words, it is now pointing back to the very same place. Let me point out, at which point it is now pointing to exactly the same place after the first decrement. In other words, if you try to look at the stack pointer right after line 6, by the time I get to here, it's going to be pointing to exactly the same place. So I'm going to say here, D points to local variable X again. So in order to store the sum of the return values of 5 and 7 into local variable X, it's really easy, right? Because it's just a store instruction because register D is already pointing to where we need it. So this can get the job done. But the problem is, what if you have multiple local variables? If you have multiple local variables, then only one of them is going to be pointed to by the stack pointer. The rest are somewhere else, okay? So if you want to make your solution more general so that it doesn't work with just the one variable that your stack pointer is pointing to, then you can do something like this, okay? There are several ways to do it. This is one way to do it. So one way to do it is to load using register C. B is fine. B has no particular use at this point, so I can use B2. But I'm going to use register C. So you're going to do it something like this. Well, what that's going to do is to say, oh, I'm just loading the immediate value of X, which is 0, into register C. Okay. And then we'll do a add instruction. We'll add register D, which is our stack pointer, to register C. So effectively what this is really doing is register C is now D plus 0. Is that okay? So I'm going to put it here just so that we can see it. So register C really is just D plus 0 because X is 0, or the way it's defined is 0. Then you can now store to what register C is pointing to with the value that we want, okay, which is in register A. So when you look at this sequence of instructions, starting from line 26, ending with line 28, this is how you generally store something into either a local variable or a parameter that is on the stack. The key to make this work is you have to have the labels defined correctly. So if you have multiple local variables, let's say X, Y, and Z, okay, then you define X, Y, and Z, accordingly, so that you can just refer to the name, the symbolic name of the variable, And the rest look exactly the same, regardless of which variable you want to access. Is that okay? Yep.
So why do we have add register C and register D if we already kind of gave C a value of 0?
Because you don't know, because you would not have known that x actually is defined to be 0. The whole is separating, the actual definition or the value of x, y, z and all the names of the local variables from the point where you make use of those names. Because the whole idea is I don't want to have to memorize, x is 0, y is 1, z is 2. I just want to give these things label names. So every time I need to access, either to read from or to write to a local variable, I can use the same sequence of code. So this way, I don't need to specialize and go like, oh, well, x is special because it is, at a 0 offset from where the stack pointer points to. So the example of having only one single local variable does not really quite convey the value of doing it this way. But if you just imagine that you have multiple local variables and they're all at different offsets from where the stack pointer points to, then it starts to make sense. Because now you can just have a general method of local variable and you don't have to mentally keep track of where they are on the stack. And I think the most important part is the local variable x, the address of that is relative to the stack pointer. X itself does not tell you where it is. It only tells you from where the stack pointer is pointing to, where is it. It is at 0 byte away from where the stack pointer points to in this particular case. So are we doing okay so far with this code? Yes? Okay. So do we want to see this run? Yeah, okay. So we'll do all this. Switch to, oh, not this one. Tempo Monkey, that's actually a really useful plugin. Which browser do I need? Not that one. Okay, I see, I hit it. Okay, there we go. So we go to the assembler. Source, and then we just delete whatever we have earlier. And paste the new program. And I'm going to call this one local var.csv. The whole purpose is to illustrate how to make use of local variables. Okay. And then we switch to the command line. And I'm going to get out of the GUI version of the of Logisim. And then we'll run it in the command line. And it's called local var.csv. There we go. Uh-oh. Cannot open file. Oh, okay. There we go. All right, so now it's done. We go back to the browser, go back to the trace analyzer. Sheet 1. And we import. The first few times you do this, it might be kind of troublesome. But the more you do it, the more you kind of remember the process, and the less difficult it would be. There we go. So we have to wait until the bar is done because, it has to go through a lot of, updates.
So, what does the label x0 line look like in the code?
Oh, that's a good question. Okay, so as it is going through this, let's go to the assemble part. So x0 means that x really is just 0. So we want to look at, when we refer to x, what does it mean? So we want to look at the LDI instruction, which is this one here, and you can see it is just loading 0, 0 into register C, which in this case doesn't seem very wise because, why would you want to add 0 to a register? Well, remember, the whole idea is, we don't know exactly what x is. Okay, when you have a larger program and you have multiple variables, then this method becomes, kind of nice because all you have to do is to remember what variable am I trying to refer to, and you just use that name.
So how does it know that it's 0?
Because I defined it to be 0. That part cannot be automatic. In other words, this definition of x being 0 has to be done by the programmer because only the programmer understands how the stack is being used.
Okay, so we can't change x later.
X is a label. A label is a static definition during the entire assembling process.
Yeah, so it's like a constant.
Yes.
Not a variable.
Yep.
Okay, that explains everything.
Okay. Is that okay?
I thought we were dealing with a variable because
No.
local
No.
variable.
X is not a variable. It is representing an offset from where the stack pointer points to the local variable that is on the stack. It's just a displacement. Yep.
What would you define a second variable? Would it just be 1?
If you define a second variable, then the offset to that is going to be 1. Now, if you define two local variables, x and y, you have a choice of whether x is 0 and y is 1 versus x is 1 versus y is 0. So you do have a choice to figure out, do you want to do things a little bit backwards, or do you want to do things the more intuitive way, which means x has a lower address compared to y.
Are the addresses arbitrary? So can you set like y to like 52?
No, it cannot be arbitrary because it has to do with how you allocate the local variable. And the allocation of local variables always happen at the entry point or the beginning of a subroutine. Yep. All right. So are there any other questions before we go to the trace analyzer? Because we want to look at the trace analyzer and find out what happens when we run this code. So are we good? Yep, go ahead.
Does that mean we'll be using position 0 on the stack, which is our no op?
No, we are going to use, okay, well, okay, let me see if I can do it this way. I'm trying to figure out a way to display both the trace analyzer and also parts of the assembler in the process. Okay, this may be good. And we'll get this one out and in its own window. That works, okay. And then get back to here. All right, so now I'm displaying, both the assembler on one side and the trace analyzer on the other side. Column C is the address, by the way. So column C is the address which corresponds to column A of the trace. So we can see 0, 0 is no op, doesn't do a single thing, no big deal. 0, 1 is our LDI instruction, to initialize the stack pointer. Doesn't do anything that we can actually see because register D is already 0 at that point. Location 3 is the label main, which is also decrement D. So with decrement D, we can see how D is decreased from 0, 0 to FF. And then the next one is 0, 4. Location 0, 4 is another decrement D, which you can also see how register D, the stack pointer, goes from FF to FE. But FF is the address of local variable X. Okay, it is the first byte on the stack that is available. And by using the decrement D over here, we are reserving that byte for the local variable. Now, the question is, why are we not storing anything right after the decrement D? Because it seems like that's really what we do. Well, it's because when you're allocating space for a local variable, it's going to come back on its own. When we are allocating space for a local variable, we are just reserving the space. We don't know what would be the value of the local variable when we declare the local variable. Does that make any sense? So we're just saying save this spot for local variable x, but I have no idea what would be the first value that we want to store. So we'll store the value later on. Okay. Okay, so scrolling down the trace analyzer. Location 5 is LDI A and then the .5 plus. So that's setting up the return address. And in doing so, you can see that register A ends up with a value of 0A. And if you look at the subroutine, which is 5, it does start at location 1A. Is that okay? So this is how you can kind of look at both the code and also the trace analyzer at the same time, and by making use of the of this particular tab, source debug. Okay. Online. So when we get into the subroutine at location 1A, all we do is to put the return value into the return value of 05 into register A, and then we put 08 into register B, because we are retrieving the return address from the stack to register B. We then increment the stack pointer because that location on stack is now used or consumed, so we can free up that space. And then we continue execution. 1E is the JMP instruction, so now we continue execution at 0A, which is the point right after JMP I to 5. So you can also double check that because this is JMP5 here in the source code. The next location is in fact 0A. So we are in fact returning to the correct location to continue the program to execute. Is that okay? All right. So right after that, at location 0A, we save the return value of calling 5 onto the stack. So we do that by first decrementing the stack pointer at location 0A, and you can see how the stack pointer is now decremented again to FE. And then we store the return value of 5 onto the stack, and you can see how 05 is now stored at location FE. Are we still doing okay so far? I mean, because are we okay? All right. So after this, I can now call 7. So the next few instructions are for calling 7. We decrement the stack pointer. We load A with the return address after 7 is done, and then we store the return address on the stack. And then we continue execution. This is the JMPI instruction to 7, and this is in 7. The first thing we do is we put the return value into register A. We retrieve the return address from 7 back to main. We increase the stack pointer. We deallocate the return address from the stack. And then we execute the JMP instruction, which then continues execution at the return address of 12 in hexadecimal. At that point, we retrieve the return value of 5 from the stack. And then we increment the stack pointer because we have just popped the return value of 5 from the stack. So now the stack pointer points back to local variable x. This is location 1.4. Okay, so location 1.4 is adding A and B because B has the return value. Yeah. So this is for popping the return value of 5, and then we compute the sum of A. Register A has the return value of 7 because that's what I just did. Register B has the return value of 5 because that's what I retrieved from the stack. By adding those two, I have 12. 12 is stored back into register A because it's add AB. And then we have, let's see, then we store. Okay, so we have load C with X. X is 0. So C is now 0, 0. And then we add the stack pointer to register C. The stack pointer is FF. When you add FF to 0, 0, it becomes FF. But we also change the flags because that's a typical add instruction. And then we store the result, which is in register A to where register C is pointing to. And then we get to the hold instruction. Yep. So the address of x is location ff for this invocation, and then the value of x when we are done with this entire program is 0c.
Right, so the value of x is stored at ff, right?
Yes. So x has an address of ff
But why do we then define x as 0?
because it is at where the stack pointer points to. Because we are trying to compute the relative distance of the various items relative to where the stack pointer is pointing to.
Okay, so then like if we had a second variable y and
Mhm.
it's defined as 1,
Yep.
its value would be at like fe.
So one would be ff, the other one would be fe. Now, which one is ff and fe is up to you to decide. So if you want to say, if you have two local variables, x and y, if you want to say x is the one that has the higher address, and then y is the one that has a lower address, that's fine. If you want to say the other way around, okay, y is the one that has a higher address and x is the one that has a lower address, that's okay too. Because it's up to you to decide how you want to allocate for your local variables. As long as you use those locations consistently, you're fine.
Okay, and then if we had a variable like na, its value would be just like 1 and fe.
Say that one more.
So if we had like stack
Right.
0, 1, 2,
Right.
and the third one, whichever one is address 2,
Right.
its value would be
One would be at an offset of 0, one would be at an offset of 1, and one would be at an offset of 2. Yep. Well, that has to do with everything that we do, all the types that we do. At this point, they're all only 8-bit integers. So by the time we get to structures, things get a little bit different because a structure can be of any particular length. So we have to factor that in when we deal with structures. But that's not for today. For today, we just deal with integers. Yep. So one more thing. Okay, we got 7 minutes, which is good. Okay. So the next one, or the next example I want to use, is something that is a subroutine, but it also has local variables. Okay. Your lab is dealing with one just like that. Okay, but I'm going to give you another one, just so that you can kind of think about how to do it. So I have to think about something that, well, it doesn't have to make perfect sense, I suppose. So we can have add again, okay, x and y, okay. Except in this case, I use a local variable called v to store x and y first. So v equals to x plus y, and then we return the value of v, okay. I understand v is not needed at all, but this is what I want to do to illustrate, what do you do when you have a subroutine that has parameters as well as at least one local variable. So we now switch to the other, just passed it. There we go. All right, so we just want to implement add at this point. The calling of add is no different from calling subtract from last week. So the caller, is going to do exactly the same thing as before. It is the subroutine itself that has to deal with the local variable. So when we have add, this is the way I would do it, okay? Doesn't mean that you have to do it this way. So I'm going to define a whole bunch of stuff, like one label for x, one label for y, one label for the return address that is also stored on the stack, and also one label for v, okay? After everything is allocated, v is going to be the one that is where the stack point is pointing to, because it is at the lowest place, because it's the last thing that we can allocate among these 4 items. The return address is going to be 1, okay? But if you want to use v1 plus, that's even better, because it is 1 byte above where v is. Y, which is pushed by the caller. Now, the ordering is a little bit off here because x is the one that has a lower address. So x is going to be return address 1 plus. And then y is the 1 byte after x, so it's going to be x1 plus. So this is how I would define the labels. And once again, x, y, return address, and v, these labels are not telling you the address of these particular items. They're telling you where these items are relative to where the stack pointer is pointing to. Okay, so you have to add the stack pointer in order to get to the actual address. Okay, but at this point, v is not allocated, okay, because the caller does not know what type of local variables are needed in the subroutine. So v is not allocated yet. So the first thing we need to do is to do a decrement d to allocate, for the local variable v. Okay, so right now at this point, okay, the labels defined are now correct. Okay, right now at this point, local variable v is where d is pointing to. The return address is 1 byte above where d is pointing to. X is 2 bytes above, and then y is 3 bytes above. Okay, so from here we can now say, okay, let's perform the addition first. I need to get to x. Okay, so we need to get x. So to get x, the typical, this is where it is nice to have these labels, because you can use a universal set of instructions to do it. So you do a LDIC with x, add CD. Does that look familiar to you? It should. Okay. So at this point, C is the address of x. But we don't need the address of x. We need x itself. So we need an LD instruction into register A or B. So this way, A is actually the value of x, not the address of x. Then we do the same thing. Okay, the next thing we need is to get y. Okay, so we say get y, LDI, CY, add CD, LD. We have to pick a different register. Okay, let's pick register B this time. So B is actually the value of parameter y, but C at this point is the address of y. Is that okay? Are there any questions? We good? Okay. So we have to compute the sum first. Okay, so we just say add AB. So now register A is x plus y. Are we good? So register A now has the value of the right-hand side of the assignment. Now it is time to compute, okay, where am I going to store it to? So we need to get the address of V to make it happen. So once again, LDI CV this time, add CD. So at this point, register C is the address of V. Once we have the address of V, then we can just do a store instruction. Okay, so we say V equals to x plus y, and that's done by a simple store instruction, because register C already has the address of variable V, and register A already has the value of the right-hand side, so a simple store instruction would do that. Are we doing okay so far with this example? If you notice that this is really kind of boring, because we have this, then we have this, and then we have this, then you're doing okay. Because that's the whole idea. This is the whole idea of why we want to define the labels, is so that we can use a very simple sequence of instructions to compute the address of items that are on the stack. Okay, so we're almost done here. And the purpose of the subroutine is to return the value of V. Now, I understand that A already has the return value, so there's no need to do anything else, other than just to do the 3 instructions to return. But if I want to stay true to the have to go to V and then retrieve it into register A and blah blah blah, which is what I'm going to do here. Oops, wrong place, wrong window. So I'll do a CV again, add CD. So at this point, C is the address of V. Then I do LEAC. So that means register A is the value of V, okay, which is what I need as a return value. And now we can return. But when you return, you have to be very careful. Where is the stack pointer pointing to at this point? Is pointing to V, okay? And where is it supposed to point to? The return address. So you have to deallocate the local variable before you do the usual sequence. So you have to do an increment d because you still have the local variable v on the stack at this point, okay? So you have to remember to deallocate the local variable v first. If you have multiple local variables, they all have to be deallocated at this point, okay? Now we're good, because at this point, register D is once again pointing to the return address. So now we can say LD, pick anything other than B, register A or register D. So register B is going to be okay. Okay, so B is the return address. Increment D to deallocate. So we deallocate return address. And then the JMPB will now continue execution to whoever caller is calling this. Is that okay? Does everybody understand, the way you access a local variable is the same as how you access a parameter? Yep.
Deallocating the parameters would happen in
The caller. Yep. So that is a minor difference compared to what I described in cisp310, because in cisp310, I kind of combine the deallocation between the callee and the caller into one single action. But in this class, we have to separate it because now we are looking at small instructions. Because x and y are arguments, are their parameters. So it is the responsibility of the caller to deallocate the arguments. So the caller deallocating the arguments is in the subtract example that we did on last Thursday. So from the caller's perspective, nothing has changed compared to last Thursday. But the subroutine's perspective has changed a little bit because now we have a local variable. So are we okay so far? Okay, so today's lab is going to be about the same thing. It will actually guide you through the very same process that I just talked about. Okay, so you just want to be a little bit slow. Okay, don't try to rush through the entire lab, during the lab time. You have 1 week to turn it in. Okay, there are more questions this time, so it might take you a little bit longer to get through that process. But the lab itself also contains the instructions, kind of like a duplicate of what we did today. So it's a kind of another exposure to these concepts. Yep.
Is it due on Thanksgiving?
Yes, it is. So I'm gonna move it to the Tuesday after after Thanksgiving. Not that most of you would actually need it, and for the people who actually will try to do it after Thanksgiving, probably cannot get it done. So try to get it done within the week, okay? Because when the concept is still fresh in your head. All right, stop the recorder.